Hi there, Mr. Holcomb here with another episode of The Math Behind the Modules. This is Lesson 7, Calculating Probabilities of Compound Events. So, classwork says a previous lesson included the tree diagrams as an effective method of displaying the possible outcomes of certain multi-stage chance experiments. Additionally, in such situations, tree diagrams were shown to be helpful in computing probabilities. In those previous examples, diagrams primarily focus on cases with two stages. However, the basic principles of tree diagrams can apply to situations with more than two stages. So here's our first example. 3 nights of games. Recall a previous example from the previous video where a family decides to play a game each night, and they all agree to use a tetrahedral die, a 4-sided die, in the shape of a pyramid, where each 4 possible outcomes is equally likely. Each night, they randomly determine if the game will be a board game B or a cards game C. The tree diagram mapping possible overall outcomes over 2 consecutive nights was as follows. So on Monday night, the possible outcomes would be a B for board game or a C for card game. Then on Tuesday, the possible outcomes could be B for a board game or C for a card game, and that could follow a Monday of a board game, and it also could follow the Monday that there possibly could have been a card game. So the outcome would be a board game and then a board game Monday and Tuesday, or a board game Monday and a card game Tuesday, or a card game Monday and a board game Tuesday, or a card game on both Monday and Tuesday. Okay. So that's not really an example, that's just review. So now it says, but how would the diagram change if you were interested in mapping the possible overall outcomes over 3 consecutive nights? So we took what we already had on Monday and Tuesday, which is here. This was our Monday and Tuesday diagram. Ran out of room on my board. Grab that again. Here's Monday and Tuesday in our diagram. Okay. And now we're going to go on to another day, Wednesday, where we're going to have a possibility of a board game or a card game following whatever occurred the previous day. Okay. So, our outcome is going to be 3 things. What happened Monday, what happened Tuesday, and what happened Wednesday. And these are all the possible outcomes. They're all different. So exercise 1 through 3 says, starting with 1, it says, if board game represents 3 straight nights of board games, BBB, what does CBB represent? That represents a card game on Monday, cards on Monday, followed by board games on Tuesday and Wednesday. Okay. CBB is card game Monday, board game Tuesday, board game Wednesday. Number 2, list all outcomes where exactly 2 board games were played over 3 days. So I'm going to look up at my outcome column, which is here. And exactly means, exactly 2 means 2 B's, not 3, not 1, not 0. So this has 3, so I'm not going to use that. Here's 2, so I'm going to write that down here. B, B, C, 2 board games. Here's another one with 2 B's. We had a board game on Monday, card game, and a board game on Wednesday. This only has 1 B. This has 2 B's. So that was a card game Monday, board game Tuesday, board game Wednesday. This only has 1 B. This only has 1 B. So now that we have finished listing them, there are 3 of them. How many outcomes were there? There were 3. Okay. Number 3. There are 8 possible outcomes representing the 3 nights, which is shown right here. So I'm going to erase this. 8 possible outcomes. 1, 2, 3, 4, 5, 6, 7, 8. Are the 8 outcomes representing the 3 nights equally likely? Why or why not? Okay. I'm going to pause the video and bring this in because it's a lengthy answer. Okay, so here we go. It says, as in the exercises of the previous lesson, the probability of C and B are not the same. As a result, the probability of the outcome C, 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 all 3 nights involved card games, is not the same as B, 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 all 3 nights playing board games. The probability of playing cards was only 1 out of 4 in the previous lessons. Okay, example 2 says 3 nights of games with probabilities. So in example 1, each night's outcome is the result of a chance experiment by rolling the 4-sided die. Thus, there's a probability associated with each night's outcome. By multiplying the probabilities of the outcomes from each stage, you can obtain the probability for each branch of the tree. In this case, you can figure out the probability of each of our 8 outcomes. For this family, a card game will be played if the die lands showing a value of 1, and a board game will be played if the die lands showing a value of 2, 3, or 4. This makes the probability of a board game B on any given night 0.75, 3 out of 4 possible outcomes. Let's use a tree diagram to examine the probabilities of the outcomes for these 3 days. Okay, so if I look at this, the probability of a B is 0.75, the probability of C is 0.25, so we put a 0.75 with every B and a 0.25 with every C, and we do that throughout. So here's a C, here's 0.25. Here's a B, here's 0.75. Now, in order to figure out the outcome of the 3 events occurring, you multiply the probabilities to get a total. So if it's a board game Monday, the probability is 0.75. Board game Tuesday is the probability of 0.75. And board game Wednesday is the probability of 0.75. So we multiply those 3 probabilities, and we come up with a value of 0.421875, which is approximately 42% of the time. So we're now going to do the exercises 4 through 6 using these outcomes. So number 4 says, probabilities for 2 of the 8 outcomes are shown. Okay, this one and this one are done for us. Calculate the approximate probabilities for the remaining 6. So if I want to know what BBC equals, I'm going to write the probability of BBC equals, okay, remember B is 0.75, 0.75 times 0.75 times probability of C, 0.25, and that equals 0.75 times 0.75 times 0.25, enter, equals 140625. Okay, a little bit more than 14%. Now I'm going to calculate the next one, the probability of BCB. Okay, well the probability of BCB is going to be the same as the probability of BBC because multiplication is commutative. I'm going to show this one time, but only this one time. The probability of B is 0.75. The probability of C is 0.25. And the probability of B again is 0.75. So all we've done was switch these two. 0.25 went here, 0.75 went here, and this one is the same. So multiplying anything, order does not matter. Multiplication is commutative. So if I plug that in the calculator in this order, I would still get 14% approximately. So there's BC. Now I'm going to do the probability of the next one, that is blank, which is BCC. So the probability of B occurring, and then C occurring, and then C occurring equals the probability of B, which is 0.75, plus the probability of C, which is 0.25, plus the probability of C again, which is 0.25. Now this is going to be a different outcome because this had 2 75s and 125, and this has 2 25s and 175. So I'm going to do 0.75 times 25 times 25. That's going to give me 0.046875. A little bit more than 4.5%. Okay, so that's BCC. Now we're going to do CBB. So I'm going to say the probability of CBB, well, that's going to equal the probability of 0.25 and then 0.75 two times. So I see that we have two B's and a C here. There's two B's and a C here. I'm going to skip over. That is going to come out to be 14% again. So that's going to be the same outcome as, and that was C. Now we're going to do CCB. So the probability of CCB equals the probability of C. 0.25 times the probability of C, 0.25 times the probability of B, 0.75. And that's going to equal, well, we have two 0.25s here and a 0.75. We have BCC here. CCB is going to come out with the same because multiplication is again commutative. So I'm going to get 0.046875 for CCB. And now, and notice that it is right here as well. The CBC was already done for us. Two C's and a B, order does not matter. We're going to get the same value every time. And now we just have to calculate C. So let me slide down here a little bit, change my color. The probability of having a card game all 3 nights is going to be the probability of C, which is 0.25 times 0.25 times 0.25. So I'm going to go to my calculator, and repetitive multiplication is exponential, so I'm going to just do 0.25 to the power of 3. 0.25 cubed is the same as 0.25 times 0.25 times 0.25, which is 0.015625. 1.5% chance of playing cards every. Okay. Number 5. What is the probability that there will be exactly 2 nights of board games over the 3 nights? So I'm going to go back. And the probability of exactly 2 nights of board games. So I'm looking for 2 B's. Probability of exactly 2 B's. So I'm going to use this one, and this one. Those are the 3 that came out to be 2 B's. Okay, so the probability of 2 B's, the probability is the same every time. It's 0.140625. Okay, so the probability of 2 board games, exactly 2. So the probability of a B, B, C, or a B, C, B, or a C, B, B, or I should just simply just say 2 board games. Probability of having 2 B's equals, and going back to the last page, 0.140625, 0.140625, they're all equal, so it's going to be just 0.140625 added 3 times, 0.140,625. Repetitive addition is multiplication, so that's 3 times repeated. So it's 0.140,625 times 3. So 0.140,625 times 3 is the same as adding it 3 times. That's going to give us 42,1875. That is 42%. Moving to decimal place. Okay. Number 6. What is the probability that the family will play at least 1 night of cards? So I want at least 1 C. So at least one night of C. This has a C, this has a C, this has two C's, a C, two C's, two C's, three C's. So the only thing I want to do is eliminate this piece. So the probability of something occurring is 100%. So the probability of at least one C means 100% minus no C's. So I'm going to do 100% minus the probability of no C's. That's how I'm going to answer this. So it's going to be 1 minus the probability of no card games equal 1 minus, and no card games is all B's, it is 0.421875. So it's 0.421875. So that is going to come out to be 1 minus 0.421875. This is malfunctioning here. Click something on my pen and I can unhook this. Okay. 0.142875. Okay, a little bit of a glitch there, but we got it. 578125. So 0.578125. Okay, here's exercise 7 through 10. A neighboring family just welcomed their third child. It turns out that all three of the children in this family are girls, and they are not twins or triplets. Suppose that for each birth, the probability of a boy's birth is 5.5 or a half, and the probability of a girl's birth is also 0.5 or 1/2 or 50%. What are the chances of having 3 girls in a family's first 3 births? Draw a tree diagram to show the 8 possible birth outcomes for a family. So they told us 8 possible births. You can have a boy or a girl. That's 2 possible outcomes. And there are 3 people that they're going to come out with is 3 kids. So a boy or a girl the first time, a boy or a girl the second, a boy or a girl the third. 2 times 2 times 2 is 8. So it wants us to use the symbol B for outcome for boy and G for girl. Consider the first birth to be the first stage. Refer to example 1 if you need help getting started. So draw a tree diagram showing 8 possible birth outcomes. So first birth I'll put here, second birth I will put here, and the third I will put here. The first could be a boy or a girl. The second could be a boy or a girl. And the third could be a boy or a girl. I need to draw this a little bit better so it fits better. Actually, I can still do this. B, like this, G, and this will be B, and this will be G. And I don't like this, so let me just draw it better. Okay, maybe if I start at the end, it'd be easier. I know there's going to be a boy, girl, boy, girl. There's going to be 8 outcomes. So this is a little bit tough to write in this space. Oh my. 1, 2, 3, 4, 5, 6, 7, 8. Okay. Yes, it is easier drawing it in reverse. Okay. There we go. Boy, boy, girl, girl, boy, girl, and then boy, girl off of that one. 1, 2, 3, 4, 5, 6, 7, 8 possible outcomes. Okay. So there is my tree diagram. Now we're going to use the tree diagram to write the probabilities of each stage and outcomes. So go back up here, and over here I'm going to write outcomes. So if I follow this branch, it's going to be B, boy, boy. All three are boys. Second branch, boy, boy, girl. So if boy, then another boy, youngest is a girl. Then how about boy, girl, boy? Middle child is a girl. And then boy, girl, girl. First is a boy, the last two are girls. And girl, boy, boy. And then girl, boy, girl. And then girl, girl, boy. And then all three are girls. Okay. So there are our 8 possible outcomes. And remember that every single one of these is 50%, 0.5, 0.5, 0.5, 0.5, and so on. There's a 50% chance it's a boy, 50% chance it's a girl, okay, so it's all listed. So the probability of getting a boy and a boy and a boy is 0.5 times 0.5 times 0.5 equals 0.125. Okay, now I'm going to save some time here. Since it's equally likely that it's a boy and or a girl, BBB, BBG, doesn't matter, 0.5, 0.5, 0.5, they're all going to add up to 0.125. I'm not going to repeat this line 8 times. They're all the same. So let's continue with the number 8. It says write in the probabilities of each stage's outcomes in the tree diagram you developed above. And determine the probabilities for each of the 8 possible birth outcomes for a family with 3 children, no twins or triplets. So that's what we did here. All the possible outcomes were 0.125. Okay, next question. What is the probability that the family having 3 girls in this situation, of a family having 3 girls in this situation? So the probability of girls, girls, girls equals, and again, it is going to be right here, and it's this, which is 0.125. There's a 12.5% chance that there'll be all girls. Is that greater than or less than the probability of having exactly 2 girls in 3 births? So, the probability of having 2 girls equals the probability of boy, girl, girl, plus girl, boy, girl, plus, that's a probability as well, plus the probability of girl, girl, and then boy. In other words, the probability of 2G is here, here, and here. There are 3 of them. Okay, so the probability of 3 girls is 0.125 plus 0.125 plus 0.125, 5, 10, 15, carry the 1, 2, 4, 6, plus that 1 is 7, 1, 2, 3, and so it's 0.375. So the probability of 2 girls is 0.375. So it says, is 0.125 greater than or less than the probability of having exactly 2 girls? So the probability of 3 girls is going to be less than the probability of 2 girls, at least 2 girls, or exactly 2 girls, because 0.125 is less than 0.375. Next question says, what is the probability of a family of 3 children having at least one girl. Having at least one girl. Probability of having at least would be 2 or 3 girls. Okay. Probability of 2 or 3 girls. At least one. So at least one, that would also be 1. Okay, so it's not 2, 3. It's going to be 1, 2, or 3 girls equals, in other words, the probability of not all boys. It's the probability of at least one girl. So that's going to equal the total probability, which is 1, minus the probability of having 3 boys. Okay? So 1 minus the probability of having 3 boys, which was 0.125. And 1 minus 0.125 equals 0.87. 87.5% chance that you'll have at least. Okay? That is the end of lesson 7. Go to your problem set.